Probability theory is all about quantifying uncertainty. Every problem starts with a random experiment, an action like rolling a die or tossing a coin, where we cannot predict the exact result with certainty beforehand. The foundation of measuring this uncertainty is the sample space, denoted by a capital S. This is a set containing every single possible outcome of our experiment. For example, if we toss 2 coins, our sample space consists of 4 distinct points: heads, heads, tails, heads, and tails. What is an event? An event is simply a subset of your sample space. If the actual outcome of the experiment falls inside that subset, we say the event has occurred. We classify these events based on their elements. An impossible event is an empty set represented by phi, such as trying to roll a 7 on a standard 6-sided die. A sure event equals the entire sample space S, like rolling a number that is either odd or even. It is guaranteed to happen every time. If a sample contains only a single sample point, it is called a simple event. If it contains more than one sample point, like getting at least one tail when tossing 2 coins, it is classified as a compound event. Algebra of Events. Just like classical sets, we can combine and manipulate events using logical operators. This is what we call the algebra of events. First, the event not A is the complement written as A dash. It includes every outcome in the sample space except the outcomes in A itself. Second, A or B represents the union, written as A union B. This event occurs if A happens, if B happens, or if both happen together. Third, A and B represents the intersection, written as A intersection B. This event occurs only if both A and B happen simultaneously. And A minus B is the set difference, which translates to A intersection B complement. Now, mutually exclusive events. Events are mutually exclusive if the occurrence of one completely rules out the occurrence of the other. Think of rolling a single die. You cannot roll an odd number or even number at the exact same time. Their intersection is completely empty, making them disjoint sets. On the flip side, a collection of events is exhaustive if their union blankets the entire sample space. This means at least one of them must happen whenever the experiment is run. If a group of events are pairwise disjoint and their total union equals S, the sample space, then they form a perfect non-overlapping partition called a mutually exclusive and exhaustive set. Next is axiomatic approach to probability. To calculate exact numerical values for these chances, mathematicians use the axiomatic approach. This framework defines probability as a function mapping an event to a real number based on 3 fundamental rules. Axiom 1 states that the probability of any event can never be negative. It must be greater than or equal to 0. Axiom 2 states that the probability of entire sure sample space is exactly 1. Axiom 3 states that if two events are completely mutually exclusive, the probability of either one happening is simply the sum of their individual probabilities. From these core rules, we can logically deduce that an impossible event has a probability of exactly 0. If I is 0. Now some key probability laws and formulas, some theorems. So let us put this theory into practice with our core calculation laws. When outcomes are equally likely, meaning every single point in our sample space has the exact same identical chance of happening, the probability of an event is simply the number of favorable outcomes divided by the total number of possible outcomes. But what if the events overlap? The addition rule states that for any two events A and B, the probability of A union B equals probability of A plus probability of B minus their intersection, probability of A intersection B.